All right, hello again, everybody. Welcome back. Today we're going to be doing section 6.7. This section is all about inverse trigonometric functions. We're going to talk about inverting those trig functions, going back and forth, doing mixed compositions with different inverse trig functions, all that good stuff. Let me go ahead and get the slides up and we'll get going. All right, so let's take a look at the overview to start. The very first thing we got to talk about is domains and ranges, and we're going to restrict some of those domains. We're going to talk about some important notes related to these inverse functions. Then we're going to go through each one by one. The inverse sine function, the inverse cosine function, inverse tangent function, inverse cosecant function, inverse secant function, inverse cotangent function. Then we'll talk about mixed compositions, mixing different inverse functions and not their inverses. And then at the very end, I've just got a summary slide that shows all the domains and ranges for the inverse trig functions. All right, so here's the first important bit. Remember that in order for a function to be invertible, it's got to be one-to-one and it's got to be continuous for it to have that inverse. Now, trigonometric functions are not one-to-one, and so they don't have inverses outright. They just fail the horizontal line test. If you remember looking at the graphs of those functions and two sections ago and the previous section, the functions are periodic. And, if you try to draw a horizontal line through them, it's going to hit many, infinitely many times, in fact. So they're not one to one, and so they're not invertible outright. However, here's the cool thing. We can make them invertible by restricting their domain, and that's what we're going to talk about in a second here. Just a general note here, whenever you're working with inverses, you really want to pay close attention to the domain and range, right? Hopefully by now you're paying closer attention to those things, just generally speaking. But when it comes to trigonometric functions, we're going to have to pay extra careful attention to the domains, particularly because we're going to be restricting them. Okay, so let's talk about the restrictions. So we're going to restrict the domains of sine, cosine, and tangent as follows. So for sine of theta, we are going to restrict the domain to the interval negative pi over 2 to pi over 2, including those endpoints. And this is just kind of a picture of what those angles would be. So sine of theta is going to be restricted to this right side of the unit circle, including these two endpoints here and here. For cosine, we're going to restrict the domain to be 0 to pi, including those endpoints. So that's this upper semicircle here. Those angles are the acceptable angles for cosine under this restriction. And then tangent, we're going to restrict theta to be between negative pi over 2 and pi over 2, but not including these endpoints, because then that would give you a vertical line, and vertical lines have undefined slope. So the idea here is whenever you are working with an inverse function of sine, cosine, or tangent, we need to have these restricted domains in order for the inverse to be defined. All right, so we're making a choice to restrict the domain of these functions to these intervals right here and these sets of angles. Now, for the reciprocal functions, it's kind of similar. So for cosecant, that's the reciprocal of sine, we're going to restrict the domain the same way we did for sine, except we're also going to cut out 0. Theta can't be 0. And again, that's just because you can't divide by 0, and sine of 0 is 0. So we need to cut that piece out. But if I flash back here for a second, yeah, you see how sine and cosecant are very similar. The only difference is that little exclusion, that little point that's popped out. Same thing with secant. So secant is the reciprocal of cosine, and the domain restriction is the same, except we're going to pop out that point right there for the same reason as we did for cosecant. We don't want to divide by 0. The one that is a bit different is actually cotangent. So cotangent, the restricted domain is going to be from 0 to pi, but not including those endpoints 0 and pi. Um, so that's the one that's like a little bit different, but it makes sense if you think about it geometrically because cotangent is the reciprocal of tangent, right? And tangent is just the slope of a line. So when we reciprocate, it's actually causing like a reflection across this diagonal line right here. So if you look at tangent, it goes from this interval, negative pi over 2 to pi over 2, to this interval, 0 to pi. And I can kind of demonstrate that to you in class if you're interested. But those are the restricted domains, okay? So focusing on the three main trigonometric functions, this is kind of the setup right here. All right, this is the setup. Sine is going to be restricted to this, cosine is going to be restricted to this, tangent is going to be restricted to this, and then these are the associated ranges with those restrictions. Now, here's an important point about those restrictions. All the values in the interval -1 to 1 are still hit by sine and cosine, even with these restrictions here. So what I mean is, even though we've restricted the domain of sine to this and cosine to that, well, the outputs of those functions are still going to be between -1 and 1, including those endpoints. So even though we've made that restriction, we're not losing any possible outputs. That's the idea. Okay. Hold on one second. All right, there we go. All right, so similarly for tangent, we're making this restriction to -pi/2 to pi/2, but we're not losing any possible output values by making that restriction. We're still going to hit every value between -infinity and +infinity when we make this restriction. So in that sense, these restrictions aren't they're not bad because we're not losing any output data. All the output data is still preserved. Okay. Now, because inverse functions invert the domain and range, we have this result for the inverse functions. Okay, so we're going to talk about each one of these in just a minute, but sine inverse, otherwise known as arcsine, has domain -1 to 1 and range -pi/2 to pi/2. They've just been switched, right? Cosine inverse, otherwise known as arc cosine, goes from -1 to 1, from -1 to 1 to 0 to pi. And then arctangent, the inverse tangent function, goes from -infinity to infinity to -pi/2 to pi/2 because they've just inverted the domain and the range. And we'll talk more about this notation in just a moment. Now, so some important notes about this. The reason those functions are called arc, you might have noticed that this is like arc sine, arc cosine, arc tangent. The reason they're called arc blah is because the output of these inverse functions is an angle that is given in radians. So this is the first important point that you want to like nestle in your brain. The output of an inverse trig function is an angle. The output is an angle, okay? And because we're using radians, the angle corresponds to the length of a circular arc on the unit circle. So that's why these are called arc sine and arc cosine and arc tangent, because what it's telling you is the length of that circular arc that corresponds to that angle given on the unit circle. So that's why they're called arc, which is pretty cool, huh? Now, here is the big idea. So inverse trig functions, they can seem confusing at first. You might even get a little bit mixed up as we're going along, but there's basically one phrase that I always use to help guide me when I'm doing these problems. And I recommend you use it too, because it just makes things very easy to evaluate. So whenever you're evaluating an inverse trig function, maybe something like arcsine, then the best method is to ask yourself this question. You say, what angle has a sine of x? Or what angle has a cosine of x? Or what angle has a tangent value of x? So you're kind of working backward. You're asking yourself, hey, what angle would give me that result that I have? And once you figure out that angle, that is the answer. That is the evaluation of the inverse trig function. All right. The other thing is each pair of a trig function and its inverse has corresponding cancellation equations. You might remember from previous when we talked about inverse functions, there are associated cancellation equations as well. So we'll go through those and I'll list them out and we'll do a couple examples along the way. Okay, now let's jump onto the inverse sine function. We'll start there. So the inverse sine function is this. It is defined in this way, this way, sorry. Might look a little bit familiar. It's kind of like what we saw when we talked about exponentials and logarithms. We say that y is equal to arcsine of x if and only if x is equal to sine of y. And here, x is in the interval -1 to 1, and y is in the interval -pi/2 to pi/2. That's basically it. And then this is the sentence. This is the sentence you want to say to yourself when you think about what arcsine is. Arcsine of x is the angle whose sine is x. So that's what you're trying to figure out. What angle has that sine value? And trust me, saying these phrases out loud, it's going to help you out a lot. It's going to make all of this very intuitive and very easy to do. Okay? Now, remember that we restricted the domain, and there's an important reason for that. You can see here that the graph of the sine function doesn't pass the horizontal line test, so it's not invertible outright, okay? That's why we restrict the domain of sine to be negative pi over 2 to pi over 2 to make it invertible. In particular, we're doing this. We're going to chop it there and there. And when we do that, if you look at this little piece of the graph on the inside here, that's one to one and it's continuous, so it's got an inverse function. Maybe I'll make this additional note. Technically, the choice of restriction to negative pi over 2 to pi over 2 is arbitrary, meaning we could have chosen a different interval, but by convention, we choose this interval. This is just the most natural restriction. Technically, we could restrict it to any number of intervals as long as we preserve that one-to-one property. Um, like, for example, we could even restrict it from here to here, right? But then that's just kind of weird because then you have to do all this modular arithmetic. You have to mod out, zero is not included in there. There's all, I mean, it's included as an output, but not as an input. It gets kind of weird, all right? So we choose the natural restriction, which is negative pi over 2 to pi over 2, and that makes everything work out just great. So here's what the graph of the sine function looks like under that restriction. So it just goes from here to here. And then because we are taking the inverse of that function, we're going to reflect it about the line y equals x, and we're going to get a graph that looks like this. So this red curve you see here, that is the arc sine function, or sine inverse. Note here as well that the domain of sine inverse is negative 1 to 1, right? And the range of the arcsine function is pi over 2 to pi over 2. Because again, those domains and ranges are getting switched from the sine function. That's it. Okay, now let's talk about evaluating them. We're going to evaluate a couple of these. Let me see which one I want to have you do first. Mhm. You know what? I will say this. I'll have you do part A first, and then I'll do part B first. So that way I can kind of show you what you have to consider in some of these cases. So for a moment here, I want you to think about this, and I want you to try to find the exact value of sine inverse of 1. So think about how you might do it. Right? And now verbalize something. Maybe say that important phrase that I just mentioned a minute ago. What is this thing equal to? What is the sentence you should say out loud? Say it out loud to give your brain that feedback, all right? All right. And now try to write it down. See if you can figure out what angle this will give. Okay. Now let's do it together. So going back to that phrase, sine inverse of 1 is the angle whose sine is equal to 1. That's what you want to say out loud. Sine inverse of 1 is the angle whose sine is 1. So what angle has a sine value that is equal to 1? And we have to remember that there's a restricted domain. So it's not just any angle we could imagine. There's only one angle in that restricted domain that will give us a sine value of 1. And as I've said many times now, you imagine the unit circle. And when you imagine the unit circle, like I've drawn here, you'll see that the angle has to be pi over 2. That's the angle, right? That is the angle in the restricted domain that has a sine value of 1. So that means that sine inverse of 1 is equal to pi over 2. Why? Well, because sine of pi over 2 equals to 1. And that is the inversion relationship right there. All right? So that's how you do that one. Okay, now for the next one, this one we have to be a little bit careful. We're going to ask the same question for this one. We're going to ask what angle has a sine of negative root 3 over 2? But again, we have to keep in mind the restricted domain. So beware. Remember, sine was restricted to this side of the circle. So we have to find an angle on this side of the circle that will have a sine value of negative root 3 over 2. And maybe when I say it like that, you can kind of imagine that it's going to be down here somewhere so that the vertical displacement, the long leg, is negative root 3 over 2. And that's exactly what that's going to be. And so that angle ends up being negative pi over 3. So here's the setup. Arcsine of negative root 3 over 2 is the angle in the restricted domain whose sine is negative root 3 over 2. In other words, this is what we're solving. This is the equation we're solving. picturing the unit circle here, we see that the angle that satisfies this is negative pi over 3. So arc sine of negative root 3 over 2 is negative pi over 3. Boom, we're done. And again, this is the inversion relationship. This is why that's occurring. So the moral here is you have to keep those restricted domains in mind, and you always want to ask yourself that question. And if you say that question, it's really going to help guide you, and that takes all the mystery out of inverting these functions. All right, next, let's take a look at the cancellation equations, right? So just like before, these inverse functions come with a corresponding set of cancellation equations. Here's the first one, sine inverse of sine of x equals x, as long as x is within that restricted domain, all right? The domains and ranges are critical here. So this cancellation equation only applies when x is in that restricted domain, all right? So beware. And again, the reason for this cancellation is what we had talked about before. You're performing a function and then you're performing its inverse, which undoes the process of that original function. And so you're left with the input that you put in at the very, very beginning. Okay. Now there's the opposite cancellation equation as well. There's the one, oh wait, hold on a second. Hold on. All right, there we go. Sorry about that. Just some technical difficulties. Where were we? Oh yeah, that's right. So now we're doing the other cancellation equation, right? So we're doing sine inverse of x and then applying sine after that, and so it's going to cancel out. But this is only true when x is in the interval negative 1 to 1. And again, that's because the inverse trig functions are defined on, or at least the inverse sine function is defined on negative 1 to 1. So pay careful attention to the domains and ranges, all right? All right, next, let's take a look at the, oh, wait, we're going to apply these cancellation equations. There we go. So how about this one? Actually, I want you to try this one first on your own, and then I'll do the next example, but try to do this one. See if you can find the exact value of sine inverse of sine of pi over 7. All right, think about it for a minute. Okay, now say something out loud, and then try to answer it on your own and write down your solution. Okay. All right, now let's do it together. So the key thing to recognize here is that pi over 7 is within the restricted domain for sine. And so that means the cancellation equation applies for this particular expression. And we can basically just cancel the sine and the sine inverse, and we're left with the answer pi over 7. So that's how we do that one. All right. Now, how about this one? I'll let you try this one actually. See if you can do this one on your own. Maybe I'll give you a little bit of a tip, but think about it for a minute. Find the exact value of sine inverse of sine of 5 pi over 7. All right. And now say something out loud, maybe something that you notice about this expression. All right. And now try to work it out on your own, and we will do it together in just a moment. All right. Okay. So let's see. Let's see, 5 pi over 7. Well, the first thing that I noticed right off the bat is 5 pi over 7 is not in the restricted domain of the sine function that we needed in order to even talk about inverse sine. So that's a problem. What that means is we cannot apply the cancellation equation that would work here yet. We can't apply it yet because this angle does not lie in that domain, that restricted domain. However, what we can do is we can be a little bit clever. We need to find an angle that is within the restricted domain that has the same sine value. And again, this is one of the beautiful things about these types of problems. They seem a little more complicated than they are, but once you can make sense of the picture and you can just think of the unit circle, it actually goes pretty quickly. So long story short, we need to find an angle that is in our restricted domain that has the same sine value. And in this case, this kind of amounts to just reflecting, reflecting that point from over here to over here. So this angle here, that is the angle 5 pi over 7, and you can see that the angle leaves the restricted domain. But if we reflect it across like so, basically subtract it from pi, then we get an equivalent, well, I shouldn't say an equivalent, we get an angle that has an equivalent sine value. So 5 pi over 7 is over here, but if we reflect the point across the y-axis, then we get this angle, which is 2 pi over 7. And 2 pi over 7 has the same sine value as 5 pi over 7. But the benefit here is that 2 pi over 7 is within the restricted domain. So now we could actually apply the cancellation equation. So maybe more algebraically, I'll say this. Sine of 5 pi over 7 is equal to sine of 2 pi over 7. Here's kind of the geometric argument here. And how did we get 2 pi over 7? Well, you can think about it like this and use the geometry, or you can think about it like this. And what we're really doing is we're looking for the supplementary angle in that sense. We're going to take pi and subtract 5 pi over 7 from it, and that actually gives us this little space right here. And that little space has the same size as that little space, those two angles. And now we can apply the cancellation equation, all right? So sine inverse of sine of 5 pi over 7 is equal to sine inverse of sine of 2 pi over 7, which is just equal to 2 pi over 7 by that cancellation equation. All right. So again, those restricted domains are critical. They're in play at all times, and we need to keep them in mind as we do these types of problems. All right, now let's talk about inverse cosine. So, very, very similar to what we just saw. The inverse cosine function is defined like so. Y equals arc cosine of x, if and only if x equals cosine of y. Again, x is in that interval -1 to 1, and y is in 0 to pi. That's our restricted domain for cosine. And then this is the phrase you're going to say out loud. Arc cosine is the angle whose cosine is x. What angle could that be in the restricted domain? That's how you work it out. So just like before, uh, the graph of the cosine function fails the horizontal line test pretty miserably. There are infinitely many points that would intersect even this one line, but we're going to restrict the domain again. We're going to restrict it to 0 to pi. Like I had mentioned before, the restriction is technically kind of arbitrary, but it's the most natural restriction to choose 0 to pi, and you can kind of see why right there. So that's what we're gonna cut the graph. And when we cut the graph, it looks like this. Boom, just like that. All right, so that is the restricted graph for cosine that will allow us to even define the inverse cosine function. Geometrically speaking, we're going to reflect this graph across the diagonal. And so we get this, which is kind of funky looking. Almost looks like some sketch of, I don't know, Jean Jacket from the movie Nope, or maybe like the aliens from the movie The Abyss or something, but or like a butterfly or something. But this is the graph of inverse cosine right here. Looks a little bit weird, but remember it's just reflected across the diagonal y equals x. You can kind of follow it if you'd like. But again, notice that here the domain of inverse cosine is -1 to 1, and the range is going to be, oops, sorry, I went backward, 0 to pi. There we go, because they're inverted, right? That's the idea. Okay, now let's do a couple examples. And you know what? You try to do both of these ones. Try to do both of these ones if you can, and then I'll walk you through them in just a moment. So think about it for a minute, see if you can find those exact values, or ponder how you would do it, I should say. And then say something out loud. You know what I would recommend, that phrase, right? Say the phrase out loud that will help guide you. All right. And now try to work it out on your own. Remember, the output here should be an angle. So you are looking for an angle. All right. Okay. Now let's do it together. Okay. So, like always, when I see these types of things, what I think to myself is, what angle has a cosine of 0? And I'm already thinking about the restricted domain. So I tend not to even say that part out loud. I'm like, what angle has a cosine of 0? Cosine is horizontal displacement. So if there's no horizontal displacement, that means the angle has to be pi over 2. So right away, I can say this is going to be equal to pi over 2. Okay, now I do the same thing for the next part. Let's see, what angle has a cosine of negative root 2 over 2. Okay, so that means the horizontal displacement is negative root 2 over 2. Okay, so if I start here, it's going to have to be in the second quadrant, right? And negative root 2 over 2, that's going to be the side length of one of those 45, 45, 90 triangles. So the picture that I'm imagining in my head looks like this. The angle's there, and this is the angle 3 pi over 4, 3/4 of pi, right? Okay, so that's 3/4 pi. 3 pi over 4. And again, that'll have a value of negative root 2 over 2, that cosine. That's our angle. And that's it. That's how you evaluate these things. So, like I had said just a moment ago, cosine inverse of 0 is pi over 2, and cosine inverse of negative root 2 over 2 is 3 pi over 4, just like that. Not too bad, right? Not too bad. Okay, just like before, there are corresponding cancellation equations. Just you got to keep those restricted domains in mind. Maybe I'll reiterate here. I don't recommend trying to memorize all of these little statements. What I recommend memorizing is the picture. Just remember the big picture, remember the unit circle, and try to imagine where that restriction is for cosine and where it is for sine and where it is for tangent, okay? And that's really all you need. That'll help guide you, right? Don't memorize everything. Memorize a little bit and then leave yourself some breadcrumbs so you can piece together the piece of bread at the end. All right, here we go. So I want you to try this one. I'm going to go a little bit fast because the idea is about the same. So see if you can figure out how to do this one. Find the exact value of cosine inverse of cosine of pi over 12. All right. And maybe say something out loud, maybe something related to restricted domains. And then write it down. What do you think this will be equal to? All right. Okay. So restricted domain, well, pi over 12 lies in the interval 0 to pi, which is our restricted domain, so we're good. So the cancellation equations apply, and this is just going to be pi over 12. That's what we're going to get, just like so. That's all it takes. Okay. Now, how about this one? All right. How about this one? You try this one also, but this is cosine inverse of cosine of negative 2 pi over 3. So think about this one for a minute. All right. Now say something out loud to help guide yourself and give your brain that feedback. And then try to write it down. All right. Okay, let's do it together. So first thing I notice here right away is negative 2 pi over 3. Okay, where is that on the unit circle? That's down here, right? That's down here or somewhere around there. It's maybe like right about there. There's that angle, but that is not in our restricted domain, which is up here. So just like before, we're going to have to find an angle that has an equivalent cosine value. And in this case, we can use the geometry again, or we can use a little bit of algebra. I always like to lean on the geometry a bit because I'm a pretty visual person. But here is that angle, negative 2 pi over 3. This is our restricted domain. So now what we're going to do is we're actually just going to reflect this point upward across the x-axis, and that's going to give us the angle positive 2 pi over 3, right? So in essence, we're just taking the opposite of the angle, and that's what you would do in the case of cosine. So instead of looking at negative 2 pi over 3, we're going to look at 2 pi over 3, and the cosine value at those two angles is equal. All right. Now remember, it's not that the angles are equal. We talked about this before, right? The angles are not equal, but the output of the cosine function at those two angles is equal. That's the idea. And that's pretty much it. Okay, so now we can actually apply the cancellation equation. So what is this equal to? Well, it's going to be equal to this because cosine of negative 2 pi over 3 is equal to cosine of 2 pi over 3. 2 pi over 3 is in our restricted domain, so the cancellation equations apply, and we get 2 pi over 3. And that's it. Pretty cool stuff, right? It's not too bad. All right. Now let's move on to the inverse tangent function. Hopefully all this is starting to sound kind of the same, a little bit like a broken record. The inverse tangent function is defined like so. So y equals arctan of x if and only if x equals tangent of y. Here, x is in negative infinity to infinity, and y is in that restricted domain, negative pi over 2 to pi over 2. And arctangent of x is the angle whose tangent is x. And so that's the phrase that you say to yourself when you want to evaluate this inverse tangent function. All right, same kind of argument as before. The graph doesn't pass the horizontal line test, so we're going to restrict the domain. You can probably, even from this picture, see what the natural choice of restriction would be. It's going to be negative pi over 2 to pi over 2. When we do that, we get this. And then for the graph of it, we're going to reflect across the line oops, that was not good. The diagonal, oh, even that wasn't so good. Okay, I'm gonna cheat. There we go. We're gonna reflect across the diagonal y equals x, and that will give us the graph of arctangent of x. So that's this one that you see right here, and it goes, but the range goes between those two asymptotes. All right, now I have this important note, and I do want you all to take note of this. Remember this for when you get into calculus 2. Arctangent is another function that we really, really love. Like we love the arctangent function. Why? Because arctangent is bounded. Arctangent is bounded, just like sine and cosine are bounded. In fact, arctangent of x is bounded between negative pi over 2 and pi over 2. And bounded functions are just great because they don't go too far. They don't deviate too far and bring in infinities and things like that. So keep this function in mind and this graph in mind when, well, in this class, but then also when you get into Calc 1 and in particular Calc 2, you will see it show up a lot there. Okay. All right, let's do the same kind of exercise here. I want you to try these ones on your own. This one might be a little bit tricky, but I want you to try to work it out, and then we'll do it together in a moment. So think about it. All right, now say something out loud, maybe that phrase, and now try to work both of them out, and we'll do it together in a moment. All right, here we go. So this one, inverse tangent of 1 is the angle whose tangent is equal to 1 in that restricted domain. So what angle has a tangent of 1? In other words, what angle gives a line that has a slope of 1? Well, if the slope is 1, it's going to be that diagonal line, right? The y equals x. And that angle is associated, or that line is associated with the angle pi over 4. So that's, oops, that's this one, pi over 4. And that's it. So inverse tangent of 1 is equal to pi over 4 because tangent of pi over 4 is equal to 1. And this is the picture that I'm imagining in my head when I do that. Now, for the next one, this one might be a little bit tricky, right? Excuse me. Here we're asking, ooh, 1 second. Ah, there we go. Wait, hold on, hold on. There we go. Sorry. Okay. Okay. This one might be a little bit hard, but the question is still the same. It's what angle will give you a line that has slope negative root 3? Okay, so there's a couple of ways to work that out, but one thing that I like to use to guide my thought process is the slope is negative, so it's going to look something like that, right? Now, negative root 3, that looks kind of familiar. That expression looks kind of familiar because I remember it from root 3 over 2, right? Root 3 over 2. So what I'm actually thinking of is an angle that looks about like this, right? So root 3 over 2, I have a feeling it's going to be negative pi over 3. And it turns out that, oops, wrong slide, that is actually correct. So arctangent of negative root 3 is negative pi over 3. This is technically y, but I want to walk through an algebraic explanation. So here what I'm doing is I'm using my intuition and I'm using some geometry to figure this out. But some algebra can be a little more clear, even if it is maybe a little more confusing. So check out this line that I've got right here. Negative root 3, we can basically multiply by a clever 1. And in this case, the clever 1 is 1/2 over 1/2. And we can rewrite this equivalently as negative root 3 over 2 over 1/2. Now, remember, in this case, tangent is sine over cosine, right? So this is sine of negative pi over 3, and this is cosine of negative pi over 3, and that's equal to tangent of negative pi over 3. So this is kind of a like a backwards algebraic way of getting to the same result, just like right here. Really what I'm doing is I'm looking for the standard angle that's associated with that root 3 idea. That's really what I'm looking for. All right. Yep. All right. And then just like before, there are associated cancellation equations for tangent. I'm not going to do an example of that here, but we will do an example of that in the activity so you can kind of chew on it and work on it on your own. But the idea is still the same. They can cancel. You just got to pay close attention to the restricted domains. All right. It's all about those restricted domains. Now, the next few inverse trig functions, I'm really just going to present and state. We will do some examples of them in the activity, but all the examples we just did, these ones would be pretty much the same. All right. They're going to be pretty much the same idea. You just ask yourself these questions and so on and so on. So the inverse cosecant function is defined as you might expect. Y equals arc cosecant of x if and only if x equals cosecant of y. Consider the ranges and the domains. And then this is that phrase, the same phrase. Arc cosecant of x is the angle whose cosecant is x. What angle could that be? Right. Then the inverse secant function, kind of the same thing. Y equals arc secant of x if and only if x equals secant of y. Keep in mind the restricted domain, keep in mind the range, and then this is the phrase that you say, arc secant of x is the angle whose secant is x. Same with cotangent, the arc cotangent function. Y equals arc cotangent of x if and only if x equals cotangent of y. And arc cotangent of x is the angle whose cotangent is x. So it's that same phrase over and over again. Okay. Now, the next thing I want to talk about is mixed compositions, because this takes a little bit more machinery to get right. Mixed compositions of trig functions, they show up a lot in math and science, doing things like, tangent of arc cosine of 1 or something like that, where you end up combining inverse trig functions and non-inverse trig functions in some way. And we want to be able to evaluate those expressions so that we can get those results and make meaning of them, right? The thing with those is that in those cases, the cancellation equations don't apply. You might have noticed that in the previous problems, the cancellation equations were working because we would have things like cosine and cosine inverse, sine and sine inverse, tangent and tangent inverse, and so they just cancel, right? Once you massage things just right. Now, for these cases where you have mixed compositions, what we're actually going to do is we're going to mix right triangle and circle trigonometry to help us evaluate these in a meaningful way. So what we're going to do is we're going to construct a triangle that exhibits the relationships given, and then we're going to find the value of the missing side of the triangle, and then we're going to use the triangle to evaluate the functions. So this is a great example of basically drawing a sketch, filling out the sketch with the information that you know, and then completing the sketch. And then you can use the sketch to answer any type of mixed composition question related to that sketch, which is pretty cool. Yeah, once again, I know I say this a lot so far, or I've said this a lot so far. The restricted domains are still in effect. Always. Anytime you are working with inverse trig functions, the first thing that should go up is a flag in your brain that says restricted domains. Consider the restricted domains. You have to consider them every single time an inverse trig function comes into play. All right. So let me do this example, and then I think I'll have you all try the next example on your own. Yeah. Let me do this one I'll just do this one outright, and then you can try the next one on your own, which is a tiny bit more challenging. So here's this one. Evaluate sine of inverse tangent of 1/2. Now, cancellation equations don't apply because this is sine and this is inverse tangent. So what are we going to do? This is what we're going to do. Keep in mind that inverse tangent of 1/2 is the angle theta whose tangent is 1/2. All right, so there's an angle that has this tangent value, and we want to know the sine of that angle. You could even think of this as this is equal to sine of theta, and we need to know what that angle is. But all we know about the angle theta is that its tangent, its tangent is 1/2. Okay, well, remember SOHCAHTOA. Or tangent is opposite over adjacent. Almost messed it up. Opposite over adjacent. So we can draw a right triangle with that relationship. Here is opposite, here is adjacent, here's theta. And now what we need to know is we want to know sine of theta. We want to know sine of that angle. What is sine? It's opposite over hypotenuse. So it's going to be 1 over question mark, 1 over c. What is c equal to? Well, if we can figure out c, then we'll be able to evaluate this whole expression. Now, we've got a right triangle at play here. So what we're going to use is we're going to use the Pythagorean theorem. The Pythagorean theorem yields that c is going to be the square root of 5. You can just go, a squared plus b squared equals c squared, and then take the square root. So this is equal to square root of 5. And now we can evaluate this expression. Sine of theta, or sine of tangent inverse of 1/2, is equal to sine of theta. Sine is opposite over hypotenuse, which is equal to 1 over root 5. There it is. Just like that. Just like that. All right. The cool thing about this particular method is once you have this triangle, you can actually answer any other expression related to taking trig functions of this angle. We could do cosine, we could do tangent, we could do I'm sorry, we could do cosecant, we could do secant, we could do all of those things, right? That's the beauty of this method. Another thing is I know some Calc 2 instructors actually teach trigonometric substitution using kind of a similar method. So some of you might actually see this again in Calculus 2. Just kind of a heads up. Sometimes it can help scaffold you for when you get there as well. Okay. Yeah, that one. Okay, now I want you to try this one on your own, and I'll give you a hint in just a moment. But think about it for a sec. Okay. Right. Now say something out loud, maybe even just read the question out loud to give your brain some feedback. And now try to work it out on your own. But I will give you a little hint here. Beware, the restricted domains are still in effect. And that will affect the way your triangle looks. Okay, that's my hint. So try it, and then we'll do it together in a moment. Okay. Here we go. So same kind of deal. This here, this is an angle whose sine is -1 over 3. And we want to find the cosine of that angle. So we're going to set up a triangle again, but the thing that we have to remember is that the restricted domains are still in play. So when I draw my triangle, I need to draw a triangle where this would even be valid to begin with, okay? So in this case, the triangle looks like that. And I'll explain why again in just a moment here. But sine inverse of -1 over 3 is the angle theta, whose sine is -1/3, and we want to know cosine of that angle. Now, since sine is negative in this case, right? Sine is equal to -1/3, our triangle is going to look like this. It's going to look like that, because remember, the restricted domain for sine is -π/2 to π/2. So if the sine value is negative, we've got to be down here in this quadrant. And that's why the right triangle appears the way that it does, just because of that restricted domain, right? Now, what is sine? It's opposite over hypotenuse. That's got to be -1. That's got to be 3. I have this intermediate step here showing that the -1 kind of gets moved up to the numerator. That's because the hypotenuse can't be a negative number, right? The hypotenuse is the length of that side of the triangle. It's also the length of the radius of the associated circle for this whole picture, right? Which I've actually got shown right here. So this is why we have that setup. Wait, let me go back. Yeah, opposite over hypotenuse. This is why we have that setup. And maybe if I kind of zoom in a bit here. Hey, 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 hey. Nope, not so fast. There we go. I can kind of zoom in so you can see. This is the way that our triangle sits in that associated circle. Here's the restricted domain for sine. And that's why our triangle appears that way. Down 1, and then here is the radius of 3. And what do we want to know? We want to know the cosine of this angle. There we go. Now we can, well, if we want to know cosine, cosine is adjacent over hypotenuse. So we need to know what A is. We're going to use the Pythagorean theorem and then go from there. Okay. All right. get back to that. So here we go. A is going to be the square root of 8 once we use the Pythagorean theorem, which is 2 root 2. And now we can evaluate any trig function associated with this triangle right here. Yeah, so cosine of sine inverse of -1/3 is cosine of this theta. That is adjacent over hypotenuse. So that's adjacent over hypotenuse, which is 2 root 2 over 3. Pretty cool stuff, huh? I just think that's cool. I like how all the right triangle trigonometry and SOHCAHTOA and the restricted domains on the circle all come together to make evaluating these things just like a very meaningful process. Not really much to memorize. You're just kind of putting the pieces together, right? Okay. One more. And I want you to try this one on your own, and we'll do it together. So think about it. All right. Now, say something out loud. Anything out loud. It could be to yourself, to your friend, to your dog, to your cat. Okay. And now work it out, and we'll do it together in a moment. All right. Okay. Same kind of deal. So let me see. Cosine inverse of -1/3 is the angle whose cosine is -1/3. Now, if the cosine value is negative, and I think about the restricted domain, that means I've got to be over here somewhere in this quadrant for that to be true. And then what is that? Cosine is adjacent over hypotenuse. So it's going to be -1 and then a hypotenuse of 3. And that allows me to construct my triangle. Here's what it looks like, just like that. So -1. Actually, you know what? Maybe I will. Oh, did I jump ahead too far? I jumped ahead too far. My bad. Here we go. Yeah. So this is my triangle, -1, and the hypotenuse is 3, just like that. Now, we want to know the tangent of that angle, the tangent of theta. So tangent is opposite over adjacent. So we're going to need opposite over adjacent, which means we got to solve for b. But again, notice here, the reason the triangle is over there is because that is what satisfies our restricted domain. Oops, that should be a 0, not an O. So the angle has to lie somewhere in this interval up here. And because cosine is negative, it's got to be over here. That's the basic idea, right? Now we can solve the triangle. So we can find the last leg of the triangle. So it's going to be 2 root 2 right here. And now tangent is opposite over adjacent. So we get -2 root 2. All right. Now I've got one more example. And I think I might, well, let's see. I'll do this one. If you want to try this one on your own, you're welcome to. But if you don't feel up for it, that's totally fine. This one's a little bit more general. But here is the basic idea. We want to try to write this as an algebraic expression in terms of u. So let me explain what this is asking. As this is written, this expression is not an algebraic expression in its nature. It's a transcendental expression, and that's because these functions, sine and tangent, they're transcendental functions. I won't go into the details of what that is, but maybe you can imagine that it's related to that definition of an algebraic number versus a transcendental number. So this expression here is in a transcendental form, and the goal here is we want to re-express it so that only algebraic expressions are involved, meaning like square roots, variables, products, sums, differences. Those are all acceptable things for an algebraic expression. So we're going to try to re-express this in an algebraic way. The good news is the technique is identical to what we just saw. All right, so that's what we're going to do. So first, inverse tangent of u is the angle theta whose tangent is u. And again, based on the restricted domain used to define the tangent function, we are going to make our triangle look like this. So tangent is opposite over adjacent. Opposite over adjacent equals u. And we're going to write u as u over 1, which is totally allowed. Any number is equal to itself divided by 1. So we can say u is u over 1. That's the opposite. That's the adjacent. Now we need to solve for c. And we can use the Pythagorean we can use the Pythagorean theorem for that again. So when we use the Pythagorean theorem, a squared plus b squared equals c squared, we find that c is going to be the square root of 1 plus u squared, just like so. So now that we have the triangle completed, we can evaluate this expression and write it in terms of just algebraic expressions. So sine of tan inverse of u is equal to sine of theta. Sine of theta is opposite over hypotenuse. Looking at this triangle, we can see that this is the opposite and this is the hypotenuse. So we get u over the square root of 1 plus u squared, just like so. And that's the idea. Okay, one last thing at the end here. I just have a bit of a summary slide. This is the summary that lists all of the inverse trig functions, all of their domains, and all of their ranges. But maybe just another word of caution here. Again, I don't recommend trying to memorize this table. That is, that's not a good mathematical practice. It's going to be tedious. It's going to be difficult. It's really easy to forget things that way. What I encourage you to do instead is to think about those pictures at the very, very beginning. Let me slide all the way back here. These ones right here. Think about these to help guide your intuition about what the restricted domains are. And then just remember what the ranges are for sine, cosine, and tangent, because and cosecant, secant, and cotangent, because we've talked about that a few times now, right? So I put this on here just as a quick reference. So if you ever just need a quick reference, it's there for you. And that's about it. So on that note, let's play. All right. It's always time to play after these things. Thank you again for listening. That's it for inverse trig functions. In the next section, we're actually going to talk about trigonometric identities, and we're going to get a lot of them, but not all of them. So I'll save the discussion for that one. Thank you all again for watching, and I will see you next time.